This is part 7 of a series on recurrent neural networks. In this video, we'll look at one of the many variations of LSTM, gated recurrent unit. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. Let's look at the structure of GRU. And let's implement many-to-many GRU models and apply them to a time series prediction problem. Let's implement a custom GRU layer and see how the output of each gate is computed, and how information from the previous time step is propagated to the next time step. And let's implement a many-to-many GRU model using Keras GRU class. Keras GRU class makes it very easy to implement GRU models. In 2014, Kyunghyun Cho et al. Proposed gated recurrent unit GRU in their paper, Learning Phrase Representations Using RNN Encoder-decoder for Statistical Machine Translation. Although the term GRU is not used in this paper, the architecture of GRU is presented in section 2.3. This paper presents the architecture of an RNN encoder-decoder model consisting of two recurrent neural networks. If we redraw this figure, it would look like this. This is also called a sequence-to-sequence network. This is a structure where sequence data is input to the encoder and sequence data is output to the decoder. This architecture can be used in machine translators or chatbots in the field of natural language processing. The output of the encoder is a hidden state H, and H is passed to the decoder. H contains the information about the input sequence of the encoder. The C in this figure is not the cell state, but the context vector. We will discuss this later in natural language processing. The authors of this paper redesigned the cell structure of this network by modifying the structure of the LSTM cell. This is what is presented in section 2.3. This was later called the gated recurrent unit. In this video, we will only cover the architecture of the GRU cell introduced in section 2.3. The RNN encoder-decoder architecture will be covered in the next series, Attention Network. Gated recurrent unit, GRU, is a variant of LSTM that improves the learning speed of the networks by simplifying the structure of the LSTM into two gates, a reset gate and an update gate. Unlike LSTM, GRU cells do not have a separate cell state C, but only a hidden state H. The gradients can flow uninterrupted through the hidden state, similar to shortcut connection in a highway network. GRU cells consist of a reset gate RT, an update gate ZT, and a candidate activation vector GT. And a GRU cell contains 3 W matrices that are multiplied by the input data X and 3 H matrices that are multiplied by the hidden state H. W is a M by P matrix and H is a P by P matrix. M is the number of features in the input data, and P is the number of hidden neurons. In addition, it contains 3 bias matrices to be applied to each gate. The bias is a 1 by P matrix. The reset gate RT is similar to the forget gate in LSTM and controls how much of the previous hidden state information is used to compute candidate activations. The candidate activation GT is new information computed with the current input X and the previous hidden state H, T-1. XT and WR are multiplied together. and HT-1 and HR are multiplied together. And the bias is added. The sigmoid activation function is applied to this result, which is the output of the reset gate, RT. The product of RT and the hidden state HT-1 is used to compute the candidate activation vector. If RT is 0, the reset gate is closed and no previous hidden state information is used when computing candidate activations. That is, the candidate activations are calculated only with the current X, regardless of the previous hidden state. The update gate ZT determines how much of the candidate activations to apply when computing the next hidden state. If ZT is 0, since this output is 1 and this output is 0, HT is kept as the previous hidden state H, T-1, and passed to the next time step. This means that there is no new information to update H at this time step. This can be expressed by the following formulas. There are two ways to compute candidate activation GT. The first way is to first compute the dot product of HT-1 and HG and then multiply the result by RT. The second method is to first multiply RT by HT-1 and then find the dot product of the result and HG. The left figure shows the second method. This document uses this formula, and this document uses this formula. HT is computed in this way. This is 1 minus ZT times H of T-1. And this is ZT times GT. This is a weighted average of H, T-1 and GT with ZT. This is similar to how we compute the cell state C of LSTM. Now let's create a GRU cell with Keras custom layer and implement a many-to-many model. Generate a time series dataset. This is the same as what we used in the many-to-many model in the previous video. Let's use this dataset to predict future time series. Now let's write a class for a GRU cell using Keras's custom layer. This has the same structure as the many-to-many peephole LSTM custom layer in the previous video. Let me explain it briefly here. In a GRU cell, there are 3 matrices W that are multiplied with the current input XT, and 3 matrices H that are multiplied with the previous hidden state H, T-1. And there are also 3 bias matrices. It has fewer parameters than LSTM. We use Keras dense layer to generate W, H, and bias as follows. These parameters are shared across all time steps. Next, we write a method to compute HT, which will be passed on to the next time step. The inputs are the current data XT and the previous state's HT-1. We use these formulas to compute the output of each gate as follows, and return HT. Next, we write the call method. This function takes data X as an input. If return sequences is true, it returns all HT stored in the list H. This is used in many-to-many models. If return sequences is false, return only the last HT stored in the list H. This is used in many-to-one models. For more details, please refer to the peephole LSTM many-to-many implementation shown in the previous video. Now let's build a many-to-many GRU model. When creating a recurrent layer, set the return sequences argument to true. This is because many-to-many models use all the outputs of each time step. And then we use the time-distributed class to create the output layer in this way. This means that the output layer is distributed across each time step. The recurrent layer has 3 W's, 3 H's, and 3 biases as trainable parameters. Each W is a 2x50 matrix, so it has 100 elements. Each H is a 50x50 matrix, so it has 2,500 elements. And each gate has 50 biases. So the recurrent layer contains 7,950 trainable parameters, which is the sum of the number of these elements. The output layer contains 102 parameters in W and B matrices. Therefore, this model contains a total of 8,052 trainable parameters. The rest of the code is identical to the code in the previous video. Let's check the results. You can see that the mean squared loss decreases significantly as training progresses. Now, let's look at the past and predicted future time series. The blue and red are the observed past time series. The green and orange are the predicted future time series. You can see that 2 sine curves with different frequencies are predicted. You can also see that the noise has been removed. Let's run this code. The results are as follows. Finally, let's implement a many-to-many model using Keras GRU class. The dataset we will use is the same as the previous code. Create a recurrent layer using Keras GRU class. Since this is a many-to-many model, set return sequences to true. And set the reset after argument to true. This is to meet the requirements of cuDNN to improve GPU efficiency. This will speed up the training process. This will use separate biases for W and H when calculating the output of each gate. The total number of trainable parameters increases. Since the number of biases increased by 3, the number of trainable parameters increased by 150. The time series prediction results are as follows. The results are similar to before. Let's run this code. The results are as follows. Let's change the reset after argument to false. You can see that the speed is slowed down like this. So far, we have looked at the structure of the gated recurrent unit and implemented the many-to-many model. In the next video, we will look at multilayer and bidirectional recurrent neural networks.